All right, for experiment 9, we're going to take a look at Young's two-slit interference experiment. Unfortunately, this really works pretty well. When I said really works pretty well. It works really well when we get the chance to use our eyeballs as the detector. It turns out that the way that this PASCO system was set up, focusing in on it with your eye and using your eye as sort of a microscope and using your retina as a viewing screen happens to allow us to see the effect pretty well. So instead of doing that, which you guys have already been through, we've already talked through it, was I grabbed a couple YouTube videos on the diffraction effect itself that was observed and known about, but was described really well by, again, there's I don't speak. I'm from I'm from Pennsylvania, so when I see how this pronounce Huy, I say Huygens or Huygens, depending on a different. I've heard it said different times. He's not around to tell us how he pronounced his last name properly. But Huygens or Huygens had an explanation as to why things happen to diffract and happen to interfere because of the wave nature, which is why we're here looking at this. But I've set this up. So here's the picture. There's the light. There's this little ruler that has this diffraction scale inside of it. And on this side, we have a component holder. So there's the component holder. There's the diffraction scale. There's the light box with light going through it. And then off we go. So it turns out the way that this number 9 is supposed to be run is we are supposed to take a look at these different size slits through these different versions of this diffraction plate. So if I get this light right over here, you'll see that this diffraction plate happens to have A, B, C, D, and E, and then on the other side, hello, it's J, I, H, G, and F. And each of these guys happens to have a different amount of lines. The thing is, I can't see it with my camera because my camera won't focus on them properly. But what we have is over here. You can see there's a very thin line there. There's a thicker line, and there's an even thicker line. We can look at some of those effects, and then what turns into there's a couple double slits. And as we turn the thing around over here, this little plate also has some multiple slits. It's very difficult to see with my camera. There they are. It looks like G has lots of lines. F has 2 lines. And this is where we can actually do Huygens' double slit experiment that we saw in the video. But you really have to use your eye to see it. But what's kind of cool about it, and how I tried to sort of explain what's going on, is rather than using these 2 slits or these multiple slits that are really far apart, so you need your eye to see this very micro effect. The optics kit also includes, you can see it doing it already, a diffraction grating. So a grating is a device that has little tiny grooves or little tiny slits. But rather than just being 2 slits and then calling it a day, this piece of plastic has been manufactured so that it has slits the whole way across. Now, the vertical slits, that's the horizontal version. This is the vertical. They have as up and down slits. And you'll notice here it says 600 lines per millimeter. So if you take 1 millimeter, which is pretty thick, and you divide it up into 600 little slits and do that continuously across this entire, what is that, about an inch, 2.54 centimeters, we get a diffraction grating. So it turns out that this works. I've discovered this works pretty well with my phone. If I put this diffraction grating on this little holder over here, which I've seen here. So this is what we're looking at without the diffraction grating. There's a little slit down there, a little hole that's letting the light through. And then there's the PASCO diffraction scale. And there's my daughter's dollhouse back there. You can see there's 15 centimeters that way, 15 centimeters this way. But if we go ahead and put this diffraction scale on here and see if I can get this guy to work and look through, all of a sudden, whoa, wait a minute, there's a rainbow on the scale. There's 2 rainbows on the scale. One is red on the out. Well, they're all red on the outside. Get this guy to focus. You can do it. Come on. Oh, there it is. Great. I'm going to stop moving my phone. So to the left, right out around 11 centimeters is the red. And then around 10, I see that turn into orange and yellow. And then at 9, I see green. And then 8, I see blue. and 7 I see indigo, and around 7.5 I see violet. And that's what's happening on the left side. And on the right side, because it's symmetric, I see the same thing going the other way, okay? And it looks like the distances are the same. It goes 7, 8, 9, 10, 11 centimeters over there, and 7, 8, 9, 10, 11 centimeters over here. But what's cool about this is if I go up higher, you'll notice that those lights aren't there. Those lights only show up because the light comes from the light box, goes through this little tiny opening. This opening is not doing the diffraction. It's just blocking out the light behind it. But when it goes through the slits of this diffraction grating, they're so close. The closer they are together, the bigger the effect. We can see that the light that is now actually forming on the electronic sensor of my cell phone. This would normally form on the sensor of your eye, but we can see this first order diffraction. There's an entire rainbow on the right side of my image on the back of my phone. I'm sure it will show up on YouTube as well. But what this allows us to do, and there seems to be another linear rainbow on the bottom that's going red, orange, yellow, green, blue, indigo, violet, sort of white in the middle underneath the slit. But this is called diffraction. So what's happening is those individual wavelets, those little tiny sources of light that are emanating as wave fronts, when they destructively and constructively interfere, they make these rainbows. So what's happening is, and we're looking through the diffraction grating, I can use my finger. My finger's still, oh, wow, look at that. My finger's going crazy. The white light, you can see, is still going straight, okay? But the white light that's in the center, there's a dark space over here before the first rainbow, okay? And then it comes over here. So what's happening is, this is really psychedelic. It turns out that in this space right here, this is all destructive interference. So we see a little bit of light. You see the white light coming through that's not diffracting. But what's happening here is that light is destructively interfering. So that's why we don't see the I have to do it this way: the red, orange, yellow, green, blue, indigo, violet. Can I do it backwards? Violet, indigo, blue, green, yellow, orange, red. I did it. It's like saying the alphabet backwards. It's Roy G. Biv. We don't see any interference here because it's destructive interference. We see constructive interference over here, but it's just the indigos and the violets that are constructing here. It's just the blues, it's just the greens, it's just the oranges, it's just the yellows, and it's yellows and the orange and the reds. And then if we were able to, I can't do it with my phone, but if I was able to move this even further, you'll see there's another rainbow way over there. It's kind of, so that's called the second order diffraction, and it's spread out even more. If you play guitar or play a musical instrument, you know that we have octaves, and all that is that's another octave. This is the first octave there. So the light itself is right in the center. This is like C, middle C, and this is the first octave, and this is the second octave over there. But you'll notice that my finger going through the diffraction grating, you see lots of versions. If I move my fingers closer back here, if I move behind the diffraction grating, you can see my rainbow hands behind it, and then now it's in front of it. Oh wow, this is really psychedelic because this is fantastic. So yeah, this is also we can do this at laser light shows or concerts. They'll hand out glasses. They're not 3D glasses, but they're diffraction glasses. We're going through Halloween here pretty soon. I know I've been to Hershey Park where we've had sweet lights where they'll hand out, you buy them for a couple bucks. They'll hand out some very inexpensive diffraction grating material like this that's inside some cardboard glasses. And when you put them on, it makes all the lights sparkle and all the lights turn into rainbows, which makes all the light display, the Christmas light display at Sweet Lights in Hershey Park, all kinds of cool. Fantastic. So this actually turned out pretty well. I've never actually performed this quote-unquote experiment or activity using my cell phone. I think I might do this in the future too, because it's kind of cool. But if we were doing this in the lab, at least as it says in the instructions, we wouldn't be doing this with a cell phone detector. We'd be using our eyes, and it would look just as awesome.